Hello, welcome back to Mr. Billingham's BC Calculus video tutorials, section 10.4, part 1, Radius of Convergence. Again, a disclaimer at the very beginning, although this is worth watching and good information, it is not within the scope of topics that will be covered on the 2020 BC exam. So I would encourage you to go over this, look over it, but don't worry about it as in terms of it covering exam topics, okay? So let's start off. Let's consider this equation here. 1 over 1 plus x squared equals 1 minus x squared plus x to the fourth minus x to the sixth plus dot dot dot. Now, I guess I want to start by reminding you that this has the form a over 1 minus r, where a is 1 and r is negative x squared. And we know that that's the formula for a geometric series. And we know that only converges when the absolute value of r is less than 1. And in this case, that would mean the absolute value of x squared is less than 1, which is equivalent to negative 1 is less than x is less than 1. So only for those numbers is this an identity. If I were to substitute a number like 1/2 into both sides, I'd have a true statement. But if I plugged a number like 2 in, well, on the left, I'd get 1/5, and on the right, I'd get 1 minus 4 plus 16 minus 64, and that certainly is not a true statement. Anyway, the radius of convergence is very important. That's the message. For the last little while, we've been looking at sine of x and cosine of x and e to the x, which converge for all real numbers. But you might remember that early on we started with a set of power series that only converged for a small interval. And so here's a look at some graphs. On the left, we show the graph of 1 over 1 plus x squared. And on the right, we show the first few partial sums of the right side. So 1 minus x squared is just a parabola. 1 minus x squared plus x to the fourth goes up and is a quartic, etc. And you notice that the interval of convergence is getting closer and closer to negative 1 to 1 if you compare the right and left graphs. So we have a theorem that's fairly important. This theorem, it's not so obvious at first, but it's important. The proof is beyond the scope of the course. And basically it says that for any power series centered at A, there are 3 distinct possibilities with respect to convergence. So, first of all, there's a positive number r such that the series diverges when x is more than r units from A. The absolute value of x minus a is more than r, but converges when you're less than r units for a. It's kind of like within a little radius. We converge within r on either side of a and diverge outside of that. Or we converge for all real numbers, or we only converge at a and diverge everywhere else. And we'll see examples of each. Well, you've seen an example of 2. Sine of x and cosine of x and e to the x converge for every real x. So the radius is infinite. And then we also saw, for instance, the last example, 1 over 1 plus x squared. It only converges when x minus 0 is less than 1. So the radius of convergence is 1. We'll see an example of number 3 in a little while. So as I've already mentioned, the number r is called the radius of convergence. And I guess the reason for that should be pretty obvious. Here's A. Here's a plus r. Here's a minus r. And this little region right here satisfies x minus a is less than r. So you can kind of see why it's like a radius. Now a pretty important test that's very simple and quite useful. This is the nth term test for divergence, and to be honest, they have it phrased kind of a little oddly. They're saying an infinite sum diverges if the nth term either fails to have a limit or the limit's different from zero. I think it's kind of nicer to consider the contrapositive. I'm going to write that down for you here. Might be a little easier to understand this way. If an infinite series converges, then the limit of the nth term has to be zero. And you should remember from earlier on that we said an infinite series converges when the limit of its partial sums converges. And if the limit of its partial sums converges, that means that the partial sums are getting closer and closer and closer as we go out. So the nth term, which would be the difference between the nth partial sum and the n minus 1th partial sum, would have to be 0 as n goes to infinity. So the weird thing is that you can use the nth term test only to test for divergence. If you try to use it to test for convergence, you don't know what you're doing. You can never use the nth term test to test for convergence. It doesn't say that if the limit of the nth term is 0, the series will converge. That's completely false. Think of the harmonic series. What it says is, if a series converges, the limit of the nth term must be 0, or if the limit of the nth term doesn't exist or isn't 0, the series must diverge. So just look at the limit of the nth term. If it's not 0, instantly you know the series diverges. So let's take a look at one of the very first tests we have for convergence of a series. We have some earlier ones, of course. We know a geometric series converges when the absolute value of r is less than 1. We know that sine of x and e to the x and cosine of x converge, for all real numbers. We've proved that. But just for two generic series, here's a way to look for convergence, and it's by comparing them term by term. The test I'm about to show you works only for non-negative series. These are series which have no negative terms. All the terms are either 0 or positive. And it allows us to determine convergence or divergence by comparing the two series term by term. So here's our theorem. So, the direct comparison test. Let sum of an be a series with no negative terms. All the terms are either positive or 0. Sum of an will converge if there's a convergent series Cn that's larger than it. So in other words, something like this. C1 is greater than A1 is greater than 0. C2 is greater than A2 is greater than 0. And so on. Cn is greater than An is greater than 0. If the C sum converges, then the A sum's trapped beneath it, and above 0, it would also have to converge. Secondly, if there's a series Dn that diverges that's trapped beneath An, then An will have to diverge also. And that should make some sense. So let's take a look at an example. My goal is to prove that this series converges by showing that it's trapped beneath another convergent series. So let's compare the terms term by term. First of all, for any x to the 2n over n factorial squared must be non-negative. X to the 2n is always x to an even power. That's got to be positive or 0 at the worst case, and n factorial squared, of course, is going to be positive. Now, this is term by term beneath x to the 2n over n factorial, because the denominators in the second one are, in fact, smaller, which makes the fraction value larger. And this second one is the same as x squared to the n over n factorial. Now we know that the power series for e to the x is 1 plus x squared over 2 factorial plus x to the n over n factorial, and we know that it converges for all real numbers. So any new power series that I could get by substituting anything in for x would also converge. And this is the power series for e to the x squared. We know it converges, and this series is term by term positive and less than it, so this series must converge. Now we have a definition and a theorem. This is going to take a moment for you to wrap your brain around. If I have some series, sum of an, which is of course a1 plus a2 plus a3, if instead I look at the series absolute value of a1 plus absolute value of a2 plus absolute value of a3, if the second series converges, then I say that the first series converges absolutely. Now I know that's going to seem a little strange, so let's take a look at an example. This should be getting familiar. This is the alternating harmonic series. We know it converges by the alternating series test, but does it converge absolutely? Absolutely not, because this is the harmonic series, and I showed you a really cool proof that this grows towards infinity. It grows without bounds. So the alternating harmonic series is an example of a series that converges, but it does not converge absolutely. When that happens, we say it converges conditionally. So, a new theorem for us. Theorem 8. If a series converges absolutely, then it converges. So it's sometimes useful, not as important as some of them, but I'm not going to go through the proof. It's pretty simple. If you want to take a look at it, it's in the book. I will show you an example of it, and that should pretty much get as much as we need to do done for this section. Let's look at the absolute value of the nth term. Now, the absolute value of sine of x is always in between -1 and 1. And if we take a look at that, it's term by term going to be less than or equal to 1 over n factorial. And 1 over n factorial well, that's the series for e, and it converges. So this is the absolute value of this. If we look at the absolute value of the terms, they are by direct comparison with e to the x less than the terms of e to the x, so it must converge. So this series converges absolutely, and therefore by our theorem it converges. Anyway, that's the end of 10.4a. Thank you very much for listening. Stay safe, stay healthy, stay entertained, keep up with your work, and look for an invite from me to have a class meeting sometime on Tuesday. Anyway, bye-bye.